This video is on Newton's second law. In an equation form, that's force equals mass times acceleration, and I call that equation 4a. Now let's first talk about the units of force. So if the units of mass are kilograms, and the units of acceleration are meters per second squared, right? If we multiply mass and acceleration, the units multiply too, and the unit we get is kilograms times meters per second squared. Now, luckily for us, we've renamed that whole mess a Newton because it's for Newton, Isaac Newton. Okay, so the units of force are newtons, and all this equation is saying is if you multiply your mass, so let's say we had 3 kilograms, and say you accelerated that 3 kilograms at 2 meters per second squared, this is saying, oh, I know how much force you must have put on that, right? You must have put 6 kilogram meter per second squared, or 6 newtons of force. 6 newtons of force are required to accelerate a 3 kilogram object by 2 meters per second squared. Cool? Okay. So let's use the same equation, 4a, and rearrange it to get us equation 4b. So 4a solved for mass, right? You tell me the mass and how much it accelerated by, and I'll tell you how much force you must have applied to it. For 4b, let's isolate acceleration by itself. So we see acceleration over here. Let's get this pesky m out of the way by dividing both sides by m. Right, what happens? Boom, boom. So we get acceleration equals force divided by mass. And so now this is saying, oh, well, if you tell me how much force you applied to an object and the mass of the object, I'll tell you how much it accelerated. So let's use the same example. So I said I used 6 newtons of force on this 3 kilogram object, and now you could tell me, oh, it must have accelerated at 2 meters per second squared. Let's think about that a little bit. This means that the higher your force is, the higher the numerator, the higher the acceleration will be. That makes sense. The more force you apply, the more the object will accelerate. The mass is on the bottom, and so that means that as the mass gets higher, right, this number will get smaller, which means the more mass the object has, the less it will accelerate for a given force. Right? So if we doubled the mass and this became a 6 kilogram object, it would only accelerate at 1 meter per second squared. And we can see, if we look back at 4a and use the same reasoning, the more mass an object has and the more you want it to accelerate, the more force you need to apply. And again, that kind of makes sense. The more mass it has and the more you want it to accelerate, the more force you'll have to apply. So let's look at equation 4c. So if we rearrange equation 4a and let's do mass by itself. What do? I gotta divide by acceleration on both sides. And my new equation is mass is force divided by acceleration. Okay, so let's again use the same numbers. If I applied a force of, if I applied a force of 6 newtons, and I got the thing to accelerate by 2 meters per second squared, how massive must it have been? Well, I applied 6 newtons of force. The thing accelerated at 2 meters per second squared. That means the thing must have had a mass of 3 kilograms. And again, you can see that this one's a little bit trickier, but if you apply a really high force, right? If you have a really high force to get it to accelerate, it means that the mass must have been really high, right? Because you had to apply such a high force to it to get it to accelerate, which means it must have had a really high mass. Alternatively, right, if it had a really high acceleration, right, you applied a force to it and it went zooming away, that means it probably had a really small mass, right? As acceleration gets bigger, this number as a whole gets smaller. So it means that for that force, if you applied a force and the thing accelerated a lot, it probably had a small mass. Cool? So this is just the general relationship of Newton's second law. And just to set us up for the next part, if we remember that A is delta V over delta T, I can rewrite the second law as force equals mass times delta V over delta T.